Yeah, I think we can start. So, good evening, everyone who is in India, and good afternoon to people from Europe. So, let me just give introduction of Paul. So, Paul is Quant of the year 2023. He, uh, he got this recognition for his innovative and thought leadership in the field of quantitative finance. He hold a PhD from Oxford and Imperial College London, and he's a visiting faculty at Imperial College. Paul has held senior roles in leading financial institutions contributing to quantitative research, algorithmic trading, and risk management. Paul worked as a quantitative researcher where he focused on derivative pricing models and risk analytics at Deutsche Bank. He has also worked in algorithmic trading and electronic market making in Citi. Then he has also worked with Nomura, and currently he is the co-founder and CEO of Thales Research. His expertise is in C++, Python, KBD, and he his expertise also in high frequency trading and low latency programming. So today's webinar agenda is basically low latency programming and high frequency trading. So yeah, welcome, Paul.
Thank you very much for the introduction. It's a pleasure to welcome you all to this lecture, and I hope that you will find it both useful and interesting. Uh, just a small correction. I have the PhD from Imperial and I have the MSc from Oxford. I didn't do another PhD at Oxford. But I did do an MSc at Oxford. Um, so I have been at Imperial maybe for like 25 years, but mostly part-time. And I've worked at a number of HFT shops. Many of them do not appear on my CV I because they're quite secretive, right? So I mean, I think the only HFT organization that does appear on my CV is Deutsche Bank, where I helped set up markets electronic trading, where I basically this is when I got involved in HFT, and then the rest of them were on the buy side, and I sort of tended not to include too much information about that in my CV. But let us talk about HFT. Presumably, that's what you guys want to discuss today. You want to discuss HFT because, well, I know why people want to discuss HFT because if you go somewhere, which is not an HFT, so if a Sharpe ratio of 2.5 will be considered good, right? And a Sharpe ratio of 3 will be considered amazing. Whereas if you go to HFT, high frequency trading, Sharps of much north of 4 and 5 can be very much the norm, at least, well, certainly north of 3 would be regarded the norm, right? So it's actually this is of a niche area where you can make very significant money. But of course, then the trade-off is that you need to enter the hardware arms race, which is not something that you need to do if you're doing conventional trading, which is basically not high frequency. Okay, so there is a barrier to it, which means you need to basically buy this very expensive equipment. But let's perhaps try and understand in the context of HFT what a microsecond is. Well, nowadays people tend to think more about nanoseconds than microseconds. But beg your pardon. At the same time, um, if you look at cryptocurrencies, collocation is very rare in cryptocurrencies, and people still talk about milliseconds because that's your network ping. That's that's the limitation. If you're not collocated, if you cannot really collocate, then you try to find something which is close to the to the actual exchange, to the hardware. Now, if you think about a microsecond, though, what Grace Hopper is holding there is a microsecond. That's the length of cable which is 300 meters, right? That's how much light travels in a microsecond. You can visualize it slightly differently. You can visualize it as the Chrysler Building. This is an Art Deco style skyscraper in Turtle Bay neighborhood on the east side of Manhattan, in New York City, at the intersection of the 42nd and Lexington. And what you see here is that it takes the building is from the antenna spire to the ground, 319 meters. Right, so so it takes like just over 1 microsecond to travel from the top of the Chrysler Spire to the ground. Okay, so that's what the microsecond looks like for light, right? But then, of course, it's difficult for information to travel truly at the speed of light within computer systems. But nonetheless, nowadays, things like MIFID II, they require you to even provide cables of equal length to different market participants. So if you are, say, a member of LSEG, then if you're a high frequency member, then the length of cabling that is given to you must match the length of cabling which is given to your competitors. That's a result of Articles 48.8 and 9 of Directive 2014/65 EU in MiFID II. And there is equivalent regulation in the UK, for example. Right, you can read up more on this, more on how collocation works at various venues. So I think this particular information is from where? This is just an article, right? The need for fair and non-discriminatory collocation services, and introduction in particular. And there is a conversation here of London Stock Exchange, and things such as BATS, ICE futures as well, Euronext. So, okay, well, let's not perhaps dwell too much on this. Let's try and look at, for a second, Linux kernel. Most of this stuff in high frequency settings will be run on Linux. Okay, and vanilla Linux can only process about, I don't know, something like 1 million packets per second. Whereas modern 10 gigabit per second NICs can usually process at least 10 million packets per second. So what can we do? Well, if the Linux kernel becomes the bottleneck, then what people would normally consider, they would consider something like the kernel bypass. And we can perform an experiment like this. On your Linux box, you can do sudo IP tables, trow, I pre-routing, and you pass all these parameters. And then what you do, you basically drop packets in Linux without hacking the kernel sources by placing a drop rule in the pre-routing IP tables chain. Okay, so you need to become a little bit familiar with IP tables to work out how to do this. Then you manipulate the indirection table on the NIC with ftool, ftool-x. So by doing that, you direct all the packets from the Rx queue, from all the packets to the Rx queue number 0. And then ftool gives you some stats, and it shows you that ftools then receives a line rate of 12 million packets per second. So, whereas the kernel can only process 1.4 million packets per second on that queue with a single CPU. Now that's a mismatch, right? So the kernel is a bottleneck now. It does not process the packets as quickly as they arrive, right? So we now ended up with this bottleneck. So the kernel has become the bottleneck. So what can we do about this? Well, let's first of all perform another experiment. So let's see the numbers when we direct packets to 4 receive queues. We can do that, right? We can do sudo f2-x f2, and we can give it equal weight and then what we can do, we can watch f2-s f2 grep rx. We basically take the output of f2 f2-s f2, and we pipe it into grep. Are you guys familiar with this? Is this something that you guys know how to do? Let me look at the chat. Okay, some of you do, some of you don't. Okay, let me kind of perhaps explain why that is the case, right? So among you, there will be people with different skill sets. Does ethanol generate packets synthetically? No, we're just looking at the packets that are arriving, right? F2, you mean? Okay, so that was a correction by this thing. So some of you will have background in networks, perhaps in cybersecurity and things like that. So some of you will be more on the hardware side, whereas some of you will be developers, right? And that is, kind of, you will have this kind of wide range of backgrounds. And for some of you, this information will be relatively standard, but for some of you, it will be new. Okay, so what we are really saying here is that it's a good idea to be aware of it, but chances are that in your organization, in your HFT, for example, there will be people who are dedicated to things like this. Okay, so just be aware that there are people with different skill sets, and this would normally be done by people who are who have a specialization in networking. And look what happens, right? So when we do this sudo f2-x, we direct the packets to 4 Rx queues, and then what happens is we still receive them at 12 point something per second, million per second, right? But then each queue is only processing 477 something, 447, 482 thousands per second. Okay, so we are now only processing something on the scale of 480 packets per second per core on each of the cores. So when the packets hit many cores, the numbers actually drop sharply. So this is perhaps contrary to what we were expecting by opening up these queues to these packets. Does that make sense? Does that make sense? Okay, so let's think about what we can do about this. And first of all, we need to have a network card that allows us to do some of this more advanced stuff. So people in the high frequency trading industry quite often use a particular type of network card called Solarflare. It's a maker of these cards. So why Solarflare? Because they support, well, there are competing products as well, but there is something known as open unload. So network doesn't support multi-threading. No. Okay, so this is not really about multi-threading. We actually have multiple cores, right? We actually have multiple cores. The issue is that we are not bypassing the kernel. Okay, so and we can achieve kernel bypass by implementing the network stack in user space. User space is the opposite of kernel space. And using an LD preload to override network syscalls of the target program. That's what we're going to do. And for low-level access to the network card, open and load relies on something known as EF_VI library. And this library can be used directly and is well documented. And basically, under the hood, each EFVI program is granted access to a dedicated RX queue hidden from the kernel. So by default, the queue receives no packets until you actually create the EFVI filter. And that filter is nothing more than a hidden flow steering rule. You will not see it in ftool-n, but the rule does exist on the network card. So once you've allocated an RX queue and managed flow steering rules, the only remaining task for EFVI is to provide the user space API for accessing the queue. Okay, user space, not kernel space API. Right, so and when you do that, you overcome this restriction. Okay, we are bypassing the kernel, right? So we're doing stuff in user space. Okay, and that's just a very quick piece of information about sort of the networking aspect of things. Let's now look at the other hardware aspects that play a big part in HFT. Right, let's look at branch prediction. Anytime there is a branch, kind of a conditional jump in your assembly code on the CPU, this is what happens. I mean, the CPU needs to predict the direction in which the branch is going to go so it can prefetch the instructions and start executing them. And quite often, this branch prediction may be incorrect, and that's going to waste quite a lot of CPU cycles, especially since nowadays CPU pipelines, they tend to be quite deep, certainly deeper than a few years ago. I mean, they're probably not as deep as the GPU pipelines, but still they are quite deep. So just so that you remember how this works, so this is the pipeline. So we see that there are a bunch of waiting instructions at time 0. None of them has entered the pipeline, but then at time 1, at clock cycle 1, we see that the green instruction is being fetched. At clock cycle 2, the green instruction is being decoded, and it is the purple instruction that's being fetched. At clock cycle 3, the green one is being executed, the purple one is being decoded, and the blue one is being fetched, and so on and so forth. Until eventually at clock cycle 5, we complete processing the green instruction as 6, the purple instruction 7, blue instruction, and 8, the red instruction. Okay, so this is what we end up with. Now, if we didn't have branch prediction, then the processor would have to stop, right, and wait until it knows the direction of the branch, right? That there would be this delay, but I mean that's not what happens. We predict the direction of the branch, we start executing the corresponding code, and if we are wrong, then we roll things back and we do it again. Okay, so there is a lot of time which is wasted on branch misprediction, and it's equal to the number of stages in the pipeline from the fetch stage to the execute stage. And modern microprocessors tend to have quite long pipelines, so that the misprediction delay can be between 10 and 20 clock cycles. So pretty long, right? So as a result, making a pipeline longer increases the need for a more advanced branch predictor. And how does that work? Well, the first time a conditional jump instruction is encountered, so we basically look at what information we have. It could be, for example, we could just start counting the frequency. I don't know what happened to this slide, but we could start counting the frequency, how often each of the branches was taken. And then we predict, the one with the higher frequency, we predict that's the branch that's going to be happening next. There are smarter ways to do it. Some people even use some rudimentary machine learning for branch prediction. But anyway, so there is this branch prediction. So we fill this pipeline with that branch, and then we roll it back and we have to recalculate stuff if we had a misprediction. Okay, so that's something that we need to be able to do. And let's move on to the, I don't know what happened to this kind of image of this branch predictor. It's not displaying correctly. But here is a question for you guys. Okay, here is a question for you. Say we are in the low latency programming setting, and we aim for a deterministic code flow, and we want to minimize branching. So we have this code flow, and my question is, how could you rewrite it with low latency in mind? Okay, so we have a bunch of safety checks. If everything is okay, we'll move on to the next safety check. If there is an error, we handle that error, perhaps display the error message. And then we keep doing this, we keep doing these checks. And at the end, if the last branch is okay, then all is fine. So can you guys tell me how we can refactor this code to minimize branch prediction, to make more optimal use of branch prediction? Can you tell me that? Try catch, in fact, will make things worse, right? Because there is an overhead associated with exceptions, right? So we're really looking here at the yeah, so carry the error until the very end, only execute at the end if fine. That's exactly right. But then how do we know what the error is? Combine them in only one condition, exactly. So instead of just having all these if statements, we will maintain some sort of like a word in memory where we set flags, which of these checks have succeeded. So we have a bunch of these safety checks, and then we look at this word or whatever it is to basically see if any of it didn't pass, and then we basically we handle all that in one place. Okay, that's exactly what you guys suggested, what Benjamin, Jose, and what a few of you have suggested. Okay, well that's a general pattern. Okay, this is how we deal with excessive branch prediction in this type of code. Okay, so then let's look at another problem that we may encounter in our code. So those of you who program in C++ will know that the moment you have even one virtual method in a class, the compiler will start creating the virtual function table for that class. Sometimes it's called vtable, sometimes called the virtual method table, but that's unimportant, right? So once we got a single virtual method, this vtable is created. In fact, well, let's have a look at this example. Class A, public void foo, void A, foo, okay. This is a class A without any virtual methods. Okay, and if we don't have virtual methods, we use static dispatch early binding. The compiler knows which routine to execute during compilation, and that's what we're also going to execute at runtime, right? So now let's make it a little bit more complex. So let me go back to the slide. We end up having this class B, where we have these two methods, bar and QX, and they just output some stuff. Okay, so then we override this by subclasses. So C overrides bar. Okay, and now suppose that we're using these classes polymorphically. So we have this B star B, a pointer. Okay, so it's not just something we're using by value, but we're using it by pointer. And we set that to a new instance of C. And then we call bar. The moment we have virtual, it will actually know to call C's bar. Okay, and this is called dynamic dispatch or late method binding. Okay, dynamic dispatch, which is an essential part of polymorphism. So this allows us to use the children of B polymorphically. And here we can set B to C by a list of principle of substitutability. So the moment we have a virtual method, the compiler will create a vtable or virtual table for us. That vtable will contain the entry for each virtual function accessible by the class, and it will store the pointer to its definition. So only the most specific function definition callable by the class is going to be stored in the vtable. So in this way, we know that we're going to be accessing C's bar and not B's bar. Okay, so that's how this this process works. I'm not sure why this is not being displayed here. I don't know. I hope that I don't know what happened to these diagrams. I mean, remind me, and I'll correct them. I mean, okay, these ones are okay. I don't know what's happening to these diagrams, but hopefully you understand what's going on. Okay, in fact, there is another pointer. There is a pointer to the vtable. There is a v pointer, which is just another class member, which is added by the compiler. It increases the size of every object that has a vtable by size of v pointer. And when a call to a virtual function or an object is performed, the v pointer of the object is used to find the corresponding vtable of the class. Okay, don't have a good diagram. It is always a good idea to add virtual destructors. In this case, make them virtual if you know always make them virtual, I guess, if you have to. Since derived classes are often handled via base class references, declaring a non-virtual destructor will be dispatched statically, obfuscating the destructor of the derived class. Okay, so here's an example. So if we have this base, which says destroying base, and we have derived, which is a destructor derived, saying destroying derived, then actually if we try to use this polymorphically, but we didn't make the destructors virtual, then we'll only get destroying base. Otherwise, we'll get destroying derived and destroying base. So if you have virtual methods, add a virtual destructor. But this is something that we do in normal non-HFT programming, right? This is our standard way of introducing polymorphism in the presence of inheritance. But what do we do if we actually have high frequency code, low latency code? Well, this introduces an overhead. We have the overhead of having v pointers. We have an overhead of having v tables at runtime. And in the low latency programming, we prefer compile time overhead. So the standard strategy for HFT code, for low latency code, is to move the overhead from runtime to compile time. So the standard strategy is to try and move quite often, when this is possible, the overhead from runtime to compile time. And how can this be done? Well, let's consider this is our classic polymorphism where we have an order, and we have specific types of orders that are inheriting from this public order, public inheritance, and generic order, which inherits from this order. Okay, and then we would have place order, but this is what we do. We use the curiously recurring template pattern. The order, as one of the template parameters, takes the actual type of the order. Okay, and in that case, we can cast this to this actual type in place order, and we can call this actual place. Okay, which would be specific then to the implementation. Okay, so it's a very clever pattern. Okay, so this saves us a lot of this runtime overhead of virtual tables, and it moves this overhead to compile time. Okay, when we can do this, and then when we create a specific order, we instantiate the order with that specific order type as the order parameter. Okay, so this approach would be preferred in the high frequency trading setting. Okay, what are the other tools that you can use in the high frequency trading setting to to make things smoother for you? Well, you could use things like microbenchmarking. As the name suggests, it's measuring the performance of something small, like a system call to the kernel of an operating system. And it's very easy to get these micro benchmarks wrong. Just as it's very easy to get the program profiling wrong. But I mean, let's look at this test loop here. The compiler will realize that your inner loop, which goes up to iter count, is not actually doing anything useful, and therefore this loop will be optimized out. Okay, so this loop is likely to be optimized out because it's not doing anything. Okay, so when you try to time how long this loop actually took, you will not get a result of that because it was optimized out. Now, suppose, okay, you're going to say, look, no, let's actually do something useful within this loop. And we're going to increment this sum in each iteration. Still, the compiler knows that the variable sum isn't used anywhere, and it will optimize it out along with the loop. Okay, so it still doesn't do anything, doesn't do what you expect it to do. And even if you then decide to print out that sum, for instance, the compiler may simply pre-compute the sum because it knows what it is and at compile time, so there is no need again to do anything. Okay. And there are more caveats associated with microbenchmarking. It's very easy to get your microbenchmarking wrong because if you are testing input-output, the operating system may preload files into memory for improved performance. You may have issues such as locality of reference. So if your data is sequential, it's likely to work faster than if your data is spread across memory. Think arrays versus linked lists. Arrays are sequential, linked lists are likely to be scattered across your memory space. Effects of caches, memory bandwidth, compiler inlining, the specific implementation of the compiler, which compiler switches you're using, the number of processor cores, optimizations at the processor level, operating system schedulers, operating system background process, all of that does affect your benchmarking. Now, profiling, you know how it differs from benchmarking. Profiling is you profile the entire thing, and typically you do it by instrumenting the code rather than benchmarking specific use cases. And that means also that you require a profiler or kind of that the tool is that you're using is first of all exists, that you have a profiler, and it will compute these whole program benchmarks with well-defined test cases. Google Benchmark is the library that most people use. It has been updated to modern C++, and it runs on GCC+, and Clang and Visual Studio. So here is an example of how you can use a benchmark. This is where you create a vector of random variates. And what do we have here? We have this cache bench. So get the size from the input, share the size between data and indices, initialize the vector with random indices, and then let's randomly access the values using these indices. So then we register the benchmark. Okay, and then we can run our main function. Our main function will be provided by Google Benchmarks. That's just a very basic example of how you can do it. But of course, let us now think a little bit more strategically. You have all these CPU cores. I mean, okay, if we are doing the computation of the CPU, each core will have its dedicated register bank. Core 1 will have its own registers, core 2 will have its own registers, and so on. And then you will have per core caches, such as level 1, level 2 in this example, and then you have shared caches across the cores. Okay, so what happens here? Why does it take, if we have a program that accesses an area of memory of a given size, And if the number of CPU cycles seems to jump at certain values, so if the area increases, why do we get the jump at 32K? What's going on? Should be quite clear what's going on. Why do we get this jump? Okay, well, thanks a lot. Is because we have run out of level 1 cache, and we now start the swapping, right? We start getting cache misses. We need to swap things in and out, and then at some point, so between 2 and 6 megs, we run out of space in level 2, and we start using level 3. Okay, so and we can see that there is a significant change in the number of CPU cycles per value. All right, that's another thing we need to know about how this stuff works. So tell me, how can we have this graph here? Can you tell me how we can improve the cache performance in this example? So maybe have a think about it for like a few minutes and put the answer in the chat. Move the no arrow at the end. Update order book with dummy data. Exactly. Okay, so you can start generating these dummy updates, fake updates, and the more they resemble the real updates, the better job you are doing at actually cache warming in this instance, in kind of emulating the flow of what happens when you have this event. And the reason you have to do it is because that's the flow that you care about, right? You don't really care about optimizing the flow where you don't have an event. You care about being efficient and at these very rare cases where you do have to send information to the network. Okay, and you do this by using cache warming. Okay, so thanks a lot. Okay, so I think this is clear. So now with this change, the order placement flow is way likelier to be in the cache. Branch prediction is also more balanced, and measurements can be used to determine how many times per unit time to perform this warm-up. Okay, so hopefully this is kind of a useful trick. And threads, again, if you program in Python, then threads are kind of limited because of the global interpreter lock. But if you program in C++, threads can be truly parallel. But if they run in the same core, then, well, they're not truly parallel. They're only interleaved. Now, you need to, of course, when you're doing this type of development, you need to be familiar with the primitives that the C++ standard library offers for these threads, right? What does it actually offer? It offers the std thread and related functions. That's a low-level access to threads. It offers mutexes, so you can lock things in critical area. It offers atomic, for example, things that you can atomically increment. So there is a large number of things that are very helpful if you want to take care of threading on your machine. So this is just a very, very basic example of using threading. You've probably done this a million times, so I'm not going to dwell on this too much. So we spawn these two threads, foo and bar. Yeah, we basically have this std thread first. We give it a function, functor. Std thread second, bar, we give it a function or functor. And we basically wait for them, we kick them off at construction, the usual C++ style. Resource allocation is initialization. Then we wait for them to join. We first pause until the first thread finishes, and then we pause until the second thread finishes. Okay, that's what we do. And then we know that the two threads have completed. But there are other interfaces in modern C++ standard library that are quite helpful for dealing with concurrency, and they work at a higher level. They are future, STD future, they are STD async, the STD package task, and the STD promise. Okay, so in case you would like to sort of step up the kind of abstraction for dealing with these things, you can start using these features of the C++ standard library, such as the future, the promise, and these are kind of two examples here of how you can do them. I'm not going to dwell on this too much because we want to really cover some of the more specific cases to do with high frequency trading and mutexes. Okay, so the problem with mutexes is that something like an STD mutex, very, very useful, creates an area that only a fixed number of threads, usually one, can enter. So this can prevent clobbering a resource, a shared resource. Think a printer. When multiple threads gain access to it, they're going to just clobber each other's work. But they introduce an overhead, right? Quite often a significant overhead. So this is an example. We introduce a mutex so that only one thread at a time can print out thread hash and the ID of that thread. Okay, so that's mutexes. Again, only one thread at any given time can be in this critical section. But people at LMAX, as we know, a while ago, have done quite a lot of research on these mutexes. And they have found that many data structures, many locked algorithms introduce unnecessary overheads. And they came up with this idea of mechanical sympathy for the hardware and creating lock-free algorithms using these kind of round-robin time buffers, type buffers. So you can look at their original talks by G and Barker. But let us just kind of conceptually think about disruptors. Let us kind of introduce this kind of disruptors as a piece of conceptual thinking. Suppose we just have this massive loop with lots and lots of iterations, and we are, for instance, just incrementing something inside this loop. Of course, we could be doing something more useful. Now, if we are doing this in multiple threads, well, foo++ is not an atomic operation, and we can get mistakes, right? How can that happen? So thread 1 comes in, reads the value of foo. Thread 2 comes in, reads the value of foo. Thread 1 with this value then increments it by 1. Thread 2 increments by 1 and writes it back. But then it's going to be incremented by 1 and not by 2. Okay, that's a typical kind of race condition. So in order really to protect this variable, say we introduce a lock. This in this example is a Java lock, which is pretty much equivalent to the C++ mutex. So the other thing we can do is introduce an atomic long and use an atomic increment. But look at what happens if we have 500 million. If we repeat this loop, then if we have one thread, then we have the overhead of 300 milliseconds. If we label the thread volatile, then it goes up 15 times, so we have 4,700 milliseconds. If we instead use the atomics, that's going to be 19 times slower. If we now use locks, that's going to be 33 times slower. If we use 2 threads now, and we use atomics, that's going to be 100 times slower. And if we use 2 threads and we use a lock, that's going to be 746 times slower and will run for 4 minutes. Okay? Do you see that there is significant overhead associated with these things, with volatile, atomic, and lock? So this is why people came up with this entire new direction in programming, which is called lock-free programming. And the idea is this: if you are programming with multiple threads, and if you do the threads access shared memory, and they cannot block each other, if your algorithm is so structured that these threads cannot block each other, then what you have created is a lock-free programming algorithm. Okay, so quite useful, and it's an interesting branch of computer science. The disruptor use case in particular assumes that there are a bunch of these queues in between the different stages of processing, right? And if you profile something like this, then you will see that a lot of the overhead comes from the queues, in fact. So the latencies at the queue stages can be substantial. And initially, you kind of say, well, it's just a problem with array-backed queues because you get this contention. If it so happens that the tail and the head basically point to the same thing, and you would say, well, probably it's likely to be better if we just use a list-backed queue. In theory, it is, but in practice, you still get contention. Even with list-backed queues. So this is where a different design pattern is basically being used, the ring buffer. And this ring buffer allows us to go parallel to basically replicate journal and do business logic at the same time, right? So this is very helpful for implementing something like a receiver and publisher type network interaction. Let me tell you maybe a few things, how you can look up more information on kernel bypass. Most of this will be in blogs, and some of these are relatively old blogs, so I do advise you guys to have a look at them. There is a bunch of videos on benchmarking, and a lot of them are very interesting. So something like Tuning C++ by Kareth, benchmarks and CPUs and compilers. So that's an interesting read. Benchmarking C++ from video games to algorithmic trading, again, an interesting read. There are a few talks on Google by Optiva that you may find very useful in your work. There are also videos on low latency C++. Many of them by Carl Cook and Nimrod Sapir. I mean, these are the guys working at HFT, so I think that it will be very useful for you guys to kind of to look at those videos. And the stuff that we have been discussing about the disruptor, you can also find some videos online on the disruptor. Okay, so you can find the lecture by Trisha G, Michael Barker. You can also look at the video by Peter Lorre, who is a practitioner, HFT practitioner. He talks about low latency code in Java 8. And another interesting video to watch is How Low Can You Go by Daniel Shire, ultra low latency Java in the real world. There are videos around low latency programming, such as on template normal programming and low latency Linux. Again, recommended for you guys to look at. There are also videos on how can you minimize latency on GPUs, and there is an interesting introduction. Sometimes people basically say, well, instead of just optimizing all of this on CPUs, let's move to FPGAs. And actually, there is a very recent book on FPGAs that, well, this book actually, that I can recommend, that it's actually, this is being blurred by my camera, but I'll tell you what it is. Getting Started with FPGAs by Russell Merrick. Quite an accessible book. And let's keep going. Hopefully these will be interesting. There are also a lot of books around low latency programming. For example, Computer Organization and Design. Okay, this is kind of just a computer architecture book. Modern Operating Systems, again, worth a read. Randall Hight's 2 volumes are outstanding. Igor Zhirkov's textbook on C is really, really interesting as well. Binary analysis again. Optimization. Optimization quite often is not concerned with latency specifically, or with jitter, or with bandwidth. So it's basically just a set of techniques that lead you to write efficient code. And you can look at real-time C++, C++ high performance, optimizing Java practical techniques for improving JVM application performance, and Scott Oak's Java performance in-depth advice for tuning and programming. Okay, let me perhaps tell you a little bit more about these patents and where you can find more information. So one of the places where you can find more information would be on my SSRN page. Let me give you the address of my SSRN page. It's here. Just give me a second. Yeah, so hopefully you can access this. Just a second. Okay, so in particular, if you go to my SSRN page, you will see that I have a number of different interests in computer science. But I think the most relevant paper for you guys will be C++ design patterns for low latency applications, including high frequency trading. So let me send you the link to that one as well. So this significantly expands on the material that I have presented. Can I use this all using Python? Well, it's unusual for Python to be used as a core high-frequency trading language. Some people are now beginning to use Rust, but Python on its own is a bit unusual. So let me tell you actually about this paper that I wrote with Burak. It's much broader than what I have been discussing today because it looks at low latency programming, design patterns. It looks at how you can optimize a market neutral trading strategy, how you can build a disruptor in C++, not necessarily an optimal disruptor. And then it considers a bunch of things. Some of them we did consider today, some of them we didn't. Cache warming, compile time dispatch, const expr, loop unrolling, short circuiting, signed versus unsigned computation, avoiding mixed float and doubles, branch prediction and reduction, slow path removal, single instruction multiple data, prefetching, lock-free programming, and inlining. So we'll look at a bunch of these things before we start looking at disruptors again. So it's not uncommon for people to invent new data structures in this setting. If you go to my SSRN page and you look at the list of papers, I think another relevant paper will be something known as semi-static conditions in low latency C++. So you can look at this one. And let's have a look at also, I think, so what did we do here? We created a new language structure. So if you have, again, conditional branches, they pose a challenge for code optimization, particularly in low latency settings. And for better performance, processors leverage dedicated hardware to predict the outcome of a branch and execute the following. The main point here is that we can actually have this pliable switch that you can alter at runtime. So you can basically say, okay, so right now we're going to do this branch, but now we're going to switch to this branch. Okay, so it's in this sense, and you can edit it fairly quickly, fairly efficiently. And we've been looking at this for quite a while with one of the HFTs, and it does bring an advantage. Then, for example, some people may instead prefer to go towards FPGAs. And you will in particular find this paper, I think, quite interesting, especially in view of the fact that people have recently been looking at uh, at the so-called DeepSeek. Yeah, I mean, I'm not actually sharing the screen. I'm just giving you some links. Let me actually read you the titles of the papers in case you're not receiving the links. So if you go to Paul Bilokon SSRN, if you Google Paul Bilokon SSRN, so the most relevant paper is C++ design patterns for low latency applications, including high frequency trading. That's my paper with Burak Gunduz. Okay, after that, I would say that semi-static conditions in low latency C++ for high frequency trading, better than branch prediction hints, could be a useful read. So what we are really talking about now is the paper on FPGAs, and it's called Optimizing Transformer Neural Network for Real-Time Outlier Detection on FPGAs. I know it mentions outlier detection in the title, but I can tell you that it can be used for other things, such as, for example, implementing LLM models on these FPGA type devices. So these are papers, these are not books, and I've just put the titles of these papers and the links to these papers on the chat as well. These are my actually they're preprints. And right, so let's see. Do you guys have any questions? Okay, so let's kind of go through. I assume many of the attendees are already working as software devs in non-HFT space. How does one break into the HFT space? It is kind of catch-22 situations. Well, read my paper with Burak. That will prepare you for the kind of things that people do in HFT. So it's definitely a good read. It was at the top of the register a little while ago. Can you share the slides? I guess the organizers will share the slides with you. Is Quant for everyone? No, I would say that only the people who are very keen to become quants. Do you have some experience on what optimizations might be required for many crypto exchange startups? Yeah, I mean, if you can get collocation, get collocation. Otherwise, optimize your location, right? You're mentioning that on AWS or some other system, try to kind of minimize your network latency because it's likely to dominate everything, right? And then once you have done that, then you can focus on other types of latency. For a quant researcher, what are the most important topics to master for HFT? So I would say low latency programming, the kind of things that we consider in that preprint with Burak. Is EFVI a library facility by software? That's correct. To kind of load your own user API to process raw network packets, it allows you. Okay, so let me kind of tell you a little bit more about how this is normally done. So it allows you to process these packets in user space as opposed to in kernel space, right? And that brings down the overhead. That prevents the kernel from slowing down the processing. Another thing that you can do, apart from working in user space, is using a dedicated FPGA. So many modern high-frequency network cards come with an off-chip FPGA, so you can try and process as many of the packets, not on the CPU even, but on this FPGA. How do you see the effects of dark pools in HFT as 50% of liquidity has moved there and it's increasing? Well, then you have to do something else. You need to do price discovery in these dark pools, right? Which can be a bit more challenging, but it's just the market is constantly evolving, right? So this is not unexpected. For a recent graduate, what is the best way to prepare for a quant dev HFT position? I have basic understanding of OS, computer networks, computer architecture, and CRTP. Again, perhaps read my preprint with Burak. There are a few books that have been published by PACT recently on HFT as well. Can we somehow try kernel bypass on our own without having solar flare NICs? It doesn't have to be a solar flare NIC. It has to be a NIC that supports this kind of technology. So if yours supports it, try it by all means. Do boost lock-free queues also use disruptor method? You mentioned before. They use something similar. I would say they use the mechanical sympathy that I've been describing. Would you happen to know about good resources on the nuances of networks used in HFT, preferably for someone with a basic knowledge of networks? Yes, I have a dedicated set of slides on networking in the HFT setting, so that it's quite a large set of slides, and we teach as part of the quantitative developer certificate program. Would it burn a hole in the packet to buy an FPGA card? Just curious. Yes. So if you buy a production one, they can cost like tens of thousands of pounds. But if you want to buy something for playing with, then I suggest you look at an inexpensive card which costs less than £200, and it will be something like AUP Pink Z2. I'm gonna add a link to the chat. Just give me a second. Okay, so hopefully you have a link now. Doesn't C++ normally add dynamic memory allocation and thus a major driver of latencies? Yes, it does. But you can even alter how dynamic memory allocation works by overloading that logic. And some people in HFT space do that. Is it also common to directly use C with pure static memory allocation instead of C++? Well, you don't need to, because you can change the logic of C++ by changing the meaning of these operators. So let me just send you this. It is quite possible to overload these things. Just added a link. Then what else? How do you envision the main developments in HFT in the future? Well, a lot of things are going on. Things are becoming faster. It's a constant arms race. It may become more difficult because your margins there are diminishing returns with as the latency fight progresses. But I mean, I'm not seeing this right now. Do you think AGI will take over the quant HFT space? It may. It's making inroads into it, and will people become redundant in the near future? I think possibly, but I don't know how near that future is. It's not sufficiently scary or active right now to scare me off, and a lot of people are still entering this space. Is it common to use custom memory allocators like TCM-malloc? Yes, it's not uncommon to do this in the HFT space. Can you suggest some good text apart from papers to gain a structured knowledge? Yes. In fact, there are I mean, there are not many texts on high frequency trading, but we can basically look at this, for instance. Let me just show you a few books on the subject. So there is this book, which is Danadia Ghosh and Rosia. So Yeah. There is another book that was published recently, and that I'll tell you exactly what it is in a minute. It's Ghosh's book. It's this one. There is also a book by Irene Aldrich, which is on HFT. But again, I do teach a pretty extensive course on these things as part of the Quantitative Developer Certificate program, not just on programming and networking. There are a fair number of lectures that I teach on this subject. Okay, well, let's see if kernel bypass NICs are not available. Would you? Well, you usually do this on specialized NICs, right? So part of the game is using specialized equipment, not just specialized NICs, but also specialized high frequency switches and so on. Can you give us a link to this quantitative program you are teaching, please? Yeah, it's called QDC. And may you please share the links for those lectures I already have. And those lectures, I don't currently have them. They're not in public domain. My lectures are not in public domain currently. Let's see. Any other questions? I have a lot of stuff in HFT that I use in teaching. I also go through the kind of the networking aspect of it. I mean, I explain how FPGAs work, how to program FPGAs, and I give a lot of C++ examples of the kind of stuff that you guys can do. Well, I hope this. I see some people have dropped off. How important is memory pooling for HFT applications? Memory management in general is very important. So, for example, you try to avoid inter-process communication as much as you can. You try to basically keep it all in memory. You try to avoid things like sockets between processes and so on. Can we make a lab setup at home to practice HFT? If yes, how? Okay, well, you can kind of build something similar to the stuff that I'm describing in the lectures. What are some pet projects we could try to implement in the context of HFT? I would say look at LMAX Disruptor, maybe port it to C++. Yeah. Have a look at the port of the LMAX Disruptor and see if you can improve it. That would be a useful exercise. For a lab setup and project building, what hardware would be needed other than FPGA? If you are just playing with something like this Pink setup, then nothing in addition to what I have described. You just need to connect it to the to your PC. Okay, so I see some people have left. It looks like I don't want to hold you up for much longer. I mean, I already gave you quite a lot of information. It's quite a specialized subject. So in case there are no further questions, I'm happy to finish here. I see quite a few people have dropped off. Okay. Thank you very much, and I hope this has been interesting for you guys. Thanks a lot. Well, have a great weekend and all the best.
Thank you very much.
Thanks a lot.
Thank you, Paul, for your time. It was a great
Thank you very
session.
much. We appreciate this opportunity. All the best.
Thanks.